Hi, I'm Norman Wildberger, and today we're going to have a look at one of the greatest innovations in mathematical history, the introduction of Cartesian coordinates in the plane by Descartes and Fermat. The main idea is to think about the plane not as an empty space, but as a grid of lines with an x-axis and a y-axis that allows us to pin down the position of any point. So for example, this point here, A, has x-coordinate 3 and y-coordinate 2, and so it's represented by the point 3, 2. Point B here is 5, 1, and so on. I've listed 5 points which all happen to be in a straight line. Besides allowing us to pin down where things are, there is a beautiful advantage that this formulation has. Euclid was actually rather vague about what a point and a line are. With Cartesian coordinates, we can define a point to be a pair of numbers. So we don't have to talk about an infinitesimally small object. We just talk about a pair of numbers. That is what a point is in Cartesian coordinates. The numbers should be thought of as displacements. They're not distances because they can also be negative. A line, say the line that goes through these 5 points, is characterized by a linear equation between x and y. So every point on this line has the property that the x-coordinate plus 2 times the y-coordinate is 7. For example, for the point A, 3 plus 2 times 2 is 7. For the point B, 5 plus 2 times 1 is 7, and so on for the other points. So, a line in Cartesian coordinates is not the motion of a particle. It's not an infinite set of points. It is an equation, a linear equation in x and y of this form. That's the definition of a line. So here are 2 lines. That's the one x plus 2y equals 7. Here's another line, x minus y equals 2, the green one. The natural question is, these 2 lines certainly appear to intersect, but they don't intersect at one of the grid points. They intersect at a point somewhere in between. So how do we find the intersection of 2 lines like that? Alright, so let's have a look at this fundamental problem of how to find the intersection between 2 lines. Here are the 2 lines, x plus 2y equals 7 and x minus y equals 2. Finding the intersection is the same as finding a pair of numbers that satisfies both of the equations. In other words, we have to simultaneously solve these 2 equations. In this particular example, we do it this way. We take equation 1 and we subtract equation 2. So the x's cancel, and we get 2y minus y is 3y equals 5. 3y equals 5. Well, then y equals 5 over 3. And then we plug that back into one of the equations, say this one, you get x minus 5 over 3 equals 2, telling us that x has to equal 11 over 3. So we found the only solution is this point here, point x, which is coordinates 11 over 3, 5 over 3. That's the intersection of the 2 lines. Another important problem is to find the equation of a line through 2 points. So here's point A, coordinates 1, 4, and here's point B, coordinates 2, 1. We would like to find the equation of the line that goes through them. To do this, we introduce another important idea, the idea of a vector or a directed line segment. We look at the line segment from A to B that has direction. It starts there and ends there. We call that a vector. And our notation is V equals AB, the little arrow above there. And to go from A to B, we go 1 over and 3 down. So in our notation, that's plus 1 followed by minus 3. But note that I'm writing this vector with round brackets now to represent that it's not a point, it's a directed line segment. This vector is the same as that vector. So a directed line segment or a vector doesn't matter where you put it, it's still the same. That vector is the same as that vector is the same as that vector. So how can we use this vector to get an equation for the line itself? Well, consider this combination of things, 3x plus y, obtained from the vector by taking that minus 3 and putting it in front of there with a minus sign and taking the 1 in front and putting it in front of a y. This combination has the property that if we add this vector to x and y, so if we add 1 to x and we add minus 3 to y, it's unchanged. That means that this is the right form for the equation of the line that has this as its direction vector. Of course, we don't know yet what the right-hand side must be. That's easy to find. Just plug one of these points in here. If we plug x equals 1 and y equals 4 in, we get 7. And to check, we plug x equals 2 and y equals 1 in, we also get 7. So the equation of the line is 3x plus y equals 7. Somewhat more generally, if we had a vector or a direction vector for a line, alpha, beta, then the equation of the line would necessarily have to have the form minus beta x plus alpha y equals something. And that would determine the direction of the line, and what's on the right-hand side would only determine where in the plane it was, but not its direction. Now here's another advantage in the Cartesian framework versus the Euclidean framework. Euclid said that two lines were parallel if they don't meet. And the way he described perpendicularity was very vague. With Cartesian coordinates, we can pin down exactly what these concepts mean. So here's some examples first. That's an equation of a line. Has that equation, 3x plus 2y equals 3. This one here, which is parallel to this one, is 3x plus 2y equals 11. And here's a perpendicular line, which is 2x minus 3y equals 3. Now let's look at the general case. Suppose we have two lines in general form. So a1x plus b1y plus c1 equals 0. a1, b1, and c1 are just three numbers. And similarly for L2. What does it mean for those two lines to be parallel? It means exactly this. That a1 times b2 minus a2 b1 equals 0. Another way of saying that is that the ratio between this and this equals the ratio between this and this. So for example, 3 to 2 equals 3 to 2. Pretty simple example in this case. So these two lines are parallel. But 3 over 2 does not equal 2 over minus 3, so those lines are not parallel. And what about perpendicular? These two lines are perpendicular precisely when this condition is satisfied. When a1 times a2 plus b1 times b2 equals 0. So for example, this line and this line are perpendicular because 3 times 2 plus 2 times minus 3 is 0. I put a star beside this definition of perpendicularity because the notion of perpendicularity is the single most important concept in geometry. It's the absolute fundamental definition in the subject. And you might wonder, why is it this form? I mean, couldn't we change this? What happens if that's a minus sign? What happens if we arrange those a little bit? Do we still get valid geometries? Turns out that we do. Later on I'll show you that there are other geometries that occur, like Einstein's geometry from special relativity, that arise simply by adjusting this definition of perpendicularity a little bit. Finally, our two main measurements. Quadrants and spread. The quadrants between 2 points is this familiar quantity here. In Cartesian coordinates, we don't have to talk about distance. It's a purely algebraic quantity. The spread between two lines turns out to be this quantity. We're going to have to talk a little bit more about this, why this definition of spread is the same as the one that we've already talked about many a time before. We'll do that in the next video. Hope you'll join me. I'm Norm Wahlberger. Thanks for listening.